So what we are going to talk about today is Fourier transform. However, we are going to go back to section 2.6 to review the Laplace transform. So recall that the Laplace transform is defined for the function, a real value function that's defined on a positive real line and is of exponential type. That means that there exists a constant c and another constant a, so that this function is goes at a rate that is not bigger than an exponential function. So the Laplace transform is defined through this formula. So the integral is with respect to t, and t is the time variable, and the s, this variable s here, is usually referred as the phase variable. Now, the key point, the key idea of the Laplace transform is that we convert a differential equation to an algebraic equation using the Laplace transform. The Laplace transform converts a differential equation into an algebraic equation, and then we solve the algebraic equation, and then we find the solution. And then but that solution is on the Laplace transform side of the equation. So it's an algebraic solution to an algebraic equation. We then use inverse Laplace transform to find the solution u, to find the little u that is a solution to the original differential equation. In this process, these are the key properties that we will use. First of all, the Laplace transform is a linear transformation. That means that it satisfies these conditions. Second of all, the derivative of a function transform under the Laplace transformation, the Laplace transform in a very nice way. So the Laplace transform of the derivative actually is just an algebraic expression, just s times the Laplace transform of the little u. So it's the differential expression on the left hand side convert to an algebraic expression on the right hand side. Likewise, you can have the Laplace transform of the second derivative is a transform in this way. By the way, you can establish this formula. We established them last time through integration by part. And then the Laplace transform of the nth order derivative is given by this formula. This you can put by integration by part and the mathematical induction principle. Now, the inverse Laplace transform map the capital U back to the little u. So that is the inverse Laplace transform. Is defined through a line integral that in the complex plane. So the idea is that you have those are the singularities of the capital US. That those are the points where the denominator is 0, where the function is not differentiable, it's not continuous. So then you draw a vertical line, real part A, and the integration is from A minus negative infinity. That means that you are integrating along this line, and then from A minus negative infinity to A plus I positive infinity. We will almost never compute the inverse Laplace transform. However, we are going to have a table, which I'm going to talk a bit later, to find the inverse transformation of the Laplace transform. Now, another property that we have talked about is the convolution. Convolution of two functions is defined through this formula here. This formula is the definition of convolution of these two functions that are defined from 0 to infinity. So remember that the integration is with respect to tau. This is a dummy variable. You can change it to c, to whatever variable that you want. The function is a function of t. Now, the good thing about the convolution, the reason that we define the convolution in this way is because under Laplace transformation, the convolution of two functions becomes just the product of two functions in the phase variable. And likewise, the inverse of the Laplace transform of a product in the phase variable in the time variable become the convolution. So convolution in time variable corresponds to products in the phase variable. And as I said a few seconds ago, that we are going to use the table of the Laplace transform to compute to find out what is the Laplace transform. So for the function 1, the simple function 1, the Laplace transform of 1 is x to negative 1, and for e to ax, the Laplace transform is 1 over x minus a, for that is true for when s greater than a, and those are the Laplace transform of these functions. And all those formulas you can compute through integration by parts or other integration techniques that you learn in calculus 2. So that when you are given the right hand side, let's say if you have this function here, then you can look at this is your Laplace transform, and then you can look at this table and you can find, oh, this is my original function in the time variable. So that is how you use the table of Laplace transforms. Okay, let's look at one specific example in this case. Let's look at example 2.11. So here you have a contaminant transport model. The differential equation is this equation is a PDE with a two variable time variable t and the spatial variable x. And this is the boundary condition. This is initial condition, and this is the boundary condition. Here we require that the solution UST is bounded. Now, so to solve this differential equation, the first thing you need to do is you apply the Laplace transform to both sides of this equation. You apply the Laplace transform to both sides of this equation. Now, notice that in this case, u is actually a function of both t and x. You have a time variable t and spatial variable x. When we define the Laplace transform, we only define it through the time variable. The spatial variable remains the same. So the integration is from 0 to infinity u t x, and then the integrate is negative s t. So we did not do anything with respect to the spatial variable. We just integrate the time variable here to get the the phase variable s here. Okay, so we apply this formula, these to the Laplace transform to both sides of the equation. Then we will have this according to the linear property, we will have this u x equals to 0. Now notice that this is, we did not the Laplace transform of USS. We do in the integral we did not do anything with respect to the spatial variable. So therefore, what you have here is UXX here. So just move it. Now, however, for the time variable, this term we go back to the previous formula that we have here. So we go back to, let me change the color now. We go back to this formula here, and then we have that this term here becomes U S X S minus U little u 0 x. Now we use this initial condition to conclude that this term here is 0. That is why we after applying the Laplace transform, we get from this equation to this equation in the phase variable. It actually is an algebraic equation, but we still have another spatial variable which is now become an ODE. So in this case, for PDE, we apply the Laplace transform and we convert the equation to an ODE with respect to the spatial variable x. Now, in this spatial variable, if you look at it carefully, that actually is a second order linear differential equation with constant coefficient. So if you ignore the phase variable, then that actually this is an equation. I rewrite it like this. Now we know how to solve this. This is ODE of with respect to x, and the characteristic equation is this. So lambda equals to positive minus square root of s. So the u, the solution we all know is going to be like as e square root of negative square root of s x plus b s e square root of s x. Now remember that we assume that this function, the solution ux, is bounded. So that means that we have to ignore this, we have to drop this term. Because this function, as x goes to infinity, this is unbounded. This is unbounded. So therefore, that is why in this case we have only this term left. Now we need to determine this as is an arbitrary function at this point. We need to determine this as through the initial condition, through the boundary condition. If we apply the Laplace transform to both of these, both sides of this boundary condition, then what we have here is going to be u 0s equals to capital Fs. So capital Fs is the Laplace transform of the little ft. So that is why that this a, if we plug x equals to 0 here, then this we will know that ax as is capital Fs. So that is why we have this solution here. Now, these are the solution in the phase variable. We need to convert into a solution in the time variable. So that means that we need to apply the inverse Laplace transform. So that we know that this capital U is a product of two functions, a product of f and product of this exponential function. So therefore, the solution, the little u, it would be the solution, little u. I write my time variable first, and then the spatial variable next. So the textbook use x and s, so that's a bit different, but it's fine. So this should be the inverse Laplace transform of capital F times, according to the formula, this formula we talk about here, the inverse Laplace transform of the product is the convolution of the inverse transform of the individual function. So this is the convolution of these two functions. Now we know that this is ft, and we need to look at the table of Laplace transform to find out what is the inverse Laplace transform of the function e to negative square root of s x times x. So we come back to this formula and we look at this item. We know that the inverse transform of a function in the form of e to negative a constant times square root of s is given by this formula, and that is why this here is given by this formula that we have here, and that is how did we arrive at this solution. Okay, just to recap what we did here. We have a PD. We apply the Laplace transform to both sides, and then we convert it to an ODE, and we solve this ODE, and then we get a solution, and then we determine this coefficient here through the boundary condition here, and then we apply the inverse Laplace transform to find the solution. Now, in applying the inverse Laplace transform, we use the table of Laplace transform from here, and we also use the fact that when we have a product of two functions, the inverse Laplace transform is the convolution of the inverse is the convolution. This is not the product, it's the convolution. Okay, so that is a brief review of section 2.6, and then we will now go next to section 2.7, that is the Fourier transform. Okay.